In this video, we're going to start talking about determinants by reviewing the determinant of a 2x2 matrix that we saw a couple videos back. So we have seen that there are many similar processes to solve a system of equations. What we don't have, which is interesting, is some sort of a general formula for solutions. And we saw this with polynomials, right? With polynomial factorization, that there wasn't really a good general way to factor everything, right? There wasn't a general formula. But unlike in that scenario, there actually is a way to solve, there is a formula for solving in general. Namely, the solutions of a system of this form turn out to have this as the formulas for x and y. All right, this is something called Cramer's rule, and we won't see, and we'll be looking more into it in a couple more videos. But this kind of gives you a motivation for why you would want to be able to do this, okay? And so to be able to do this in general, we kind of need to follow some patterns here, and we're going to need a definition. So here we define the determinant of the matrix A equal A1, B1, A2, B2 as given by the determinant of A, which is equal to, this is also read as the determinant of A, so it's kind of like a size sort of thing. Namely, we also have the bars, so I want you to notice the bars here. This isn't like the matrix, right? These are bars which are telling you to take the determinant, so to speak. And so here we have A1 times B2, namely we do those minus those two multiplied. And if you've been keeping up with the videos, this isn't new. This is what we used to calculate the inverse of a 2x2 matrix. Now, again, I want you to notice that the solution to the system, kind of going back to the last slide, the solution to the system was, to this system that with this augmented matrix was then C1, C2, B1, B2 over the determinant of the matrix A, okay? Namely, we took the determinant of this top matrix, but we did it in a way where we replaced the column A1, A2 by C1, C2 for X. So we replaced sort of the first column. We replace the second column with C1 and C2, and using the exact same thing otherwise, we get Y. And so this notation is actually pretty useful for calculating with. And it's also not too hard to calculate with, again, because all you have to do is A1, B2 minus B1, A2. So for example, if we wanted to find the determinant of A, we would have the determinant of A is equal to 2 times 2 minus 1 minus negative 3 times 1. So that's going to be 4 plus 3, so 7. We also, if we were going to calculate the determinant here, we would have the determinant of B is 2 times 2 minus 1 times 4, which is 4 minus 4, so 0. And then finally for C, we have 0 times 4 minus 3 halves times 2. Here 0 and 4 is 0. 3 halves times 2 is 3, so we get negative 3. And this is interesting because it shows you that the determinant can be positive, negative, or 0. So there are all sorts of options. And now it's your turn to try this out. So go ahead and find the determinant of each of the following matrices. On the count of 3, I will reveal the solution to all of them. 1, 2, 3. So here the determinant of the matrix A is negative 7, the determinant of the matrix B is 10, and the determinant of the matrix C is 0. For more practice in computing these simple 2x2 determinants, be sure to see page 582 of the textbook. And in our next video, we're going to try to start expanding towards being able to do determinants of bigger matrices by looking at minors and cofactors.